Today, Meta is revealing prototype VR headsets that explore the benefits and limits of display resolution, optical focus shifting, brightness, and headset form factors. We had the opportunity to visit Reality Labs research to go hands-on with these prototypes, and also sat down with Meta CEO Mark Zuckerberg to learn how these experiments are important steps along the way to VR passing what he calls the visual Turing test.
So I'm excited to be here with you. This is an interesting area of research. We're talking about displays and how to have a virtual and augmented reality display that can ultimately pass the visual Turing test, right? So it's this sense of, this qualitative sense of having a display that feels indistinguishable and at the quality level of a physical environment. And of course, when you're building these headsets, there are a lot of different parts of them that go into them. The display is just one piece. You also have, all of the software and the silicon and the sensors and the other hardware components. But in the Reality Labs research group is working on advancing all of those. What we do, we basically break our work down into, we have product teams that are working on, a few generations of Quest going forward. And then we have the research team, which is basically trying to break down barriers and solve fundamental technology problems that are going to be necessary for the future versions of Quest and the AR glasses and things like that we want to ship, maybe in the second half of this decade. So these two efforts kind of work together. Today we're focusing on displays, and we're talking about basically all of the different dimensions that you need to achieve breakthroughs in order to deliver this sense of realism, right, and pass the visual Turing test. And this is a much more complex problem than producing a high-quality traditional display like what you'd have on a TV or a computer monitor or a phone for a number of reasons. I mean, some of the dimensions are similar, right? You have things like resolution. You want to get it to be sharp, right. But even that, it's harder because the kind of angle of your field of view in a VR or AR system is just so much wider than what you have on a phone, right, or even a big TV. So it just ends up being way more pixels and harder to power. But then you have things like you want it to be 3D, so you need it to be stereoscopic. You need two screens. Unlike in a computer monitor, it's at a fixed place on your desk, and you're focused on one plane. In virtual or augmented reality, objects come into your view that are at different planes. And when you're reading a book, your eyes focus very close. If you're looking at the detail on leaves of a tree or something in the landscape, you focus further out. And our eyes kind of move and they flex in order to focus. But you need to be able to do that for these kind of displays. So you get into challenges like that that are just different from what anyone has solved before, as well as I know one of the demos that you saw was Starburst for basically HDR, right? It's in the sense of, just the light that we take in from the physical environment. It's like an order of magnitude more than what even the highest quality traditional displays or HDR TVs or really high quality monitors have today. And if you really want, it to feel like the shadows are real or the colors are vivid when you're looking at the landscape, you just need a lot of light. And that means that you need a lot of power, but then you need to be able to power that all from a battery that you have on a small device on your head. So these are all things that we need to advance. And that's kind of the scope of what the display research team is working on.
Yeah, so as I understand it, it's a research team. They kind of have this runway to look into the future and think about all the things that we take for granted with our eyes in the real world. And VR, I think, does a great job today of creating believability in virtual environments, the sense of presence. But I'd love to talk more about the difference between presence and passing the visual Turing tests. Is the idea that these environments and the experiences are photoreal, or what do you see as kind of the benchmark for the visual Turing test?
Yeah, so for the visual Turing test, I do think you need to get to more photoreal. I think it's worth noting that having a sense of presence, which is the key feeling that we talk about in virtual and augmented reality, is that unlike all other screens or computing platforms before, you feel like you're there with a person or in another place, and you can start to deliver glimpses of that even without passing the visual Turing test. But I think undoubtedly, as you get closer to actually having that kind of fidelity, it'll just get better and better. So I think today about experiences like workrooms. I don't know if you've had a chance to play around with this yet, but I compare, what the experience in workrooms to like a normal Zoom call. And even though the fidelity of the avatars today isn't photorealistic, there are still things that actually in some ways feel like a much better sense of presence in workrooms because you have a shared sense of space. There's spatial audio. You can be in a meeting, you can turn to the person next to you and whisper, right? These are all things that you can't really do on a Zoom call. So I think as we get closer to photorealism and closer to the visual Turing test, that sense of social presence will just get even stronger. And at the end of the day, that's why Meta is working on this. I mean, we're the social technology company that's focused on how people connect. And these are all pretty deep problems that are going to go towards a lot of different ways about how we choose to express ourselves and our identity and how we connect.
Doug, it's such a pleasure to meet you. Thank you so much for having us here.
Yeah, thanks, Norm. I've really been looking forward to this. Been following you for years, and we keep thinking, like, when's the moment we can invite Norm?
Now we've been secretly thinking the same thing. When's the moment you can invite us?
Great. Well, I mean, it's really exciting to have you here today, I think, showing you all the work we've done, but not just the demos and these cool headsets, but what's inside and how much we work to bring these things together and, how hard it is.
Can you give me like the overview of what we're seeing here and what this represents?
Yeah, absolutely. So I've been here for 7 years, and over that time, we've built up this team I lead now called Display Systems Research. So you're going to see those three things. Displays, so this big wall of headsets sort of is indicative of the type of work we do. You've heard of this, probably your audience has. We've been working on varifocal headsets for many years. And that gave birth to this ethos in our team to just demo it, to build it, to show it. And so you sort of see how it has expanded in the last few years to a lot more. And all of this is a glimpse of, I think, potential futures in 5 to 10 years.
So here's basically the version of what we've put together. It's sort of a modified Rift, but what's different is that instead of having the lenses fixed at in a certain position, we're able to actually move them around, right? So it's almost like how autofocus would work on a camera, for example. And the way that this works is, if you're reading a book, your eyes focus closer. If you're looking out at the horizon, your eyes focus out there. Most current VR displays are set to focus about 5 or 6 feet out. So that way, first of all, a lot of what we interact with is sort of in that range, but it also, you can look a little past it and it's comfortable. But if you try to focus on something that's really close, your eyes try to focus in on that, and it doesn't actually. The screens don't actually have the ability to focus at a closer range than that, so it maybe feels a little blurry and it fatigues your eyes a bit. But what we're working on here with Half Dome is the ability to basically have an optical stack that basically you can activate different lenses to either focus at a nearer or further distance. And then if you have a number of those lenses stacked, then you can kind of activate them in different combinations to basically have a pretty dynamic range of how you can focus. So we're trying to reduce the kind of mechanically, physically moving components in it. I mean, the simplest way to do this is literally to have a lens that moves back and forth. But having it more electrically actuated, reduces the kind of mechanical movement and also just makes it so that you can activate it a lot quicker than having to physically move the lens. So that's kind of where we are in the research on this. It's there's still quite a bit of work that we would need to do before this will ship in a product, but compared to some of the other dimensions like HDR that I think are still quite far out, I think we have a reasonable shot at shipping something with varifocal technology, in say, the next 5 or 6 years. So I mean, don't hold me to that exactly. I mean, it's obviously hard to get the stuff into products, but at least that's the hope based on where we are now.
So Doug, this is Half Dome 1?
Yep, really excited to show you. You're in the room where we actually built this, where I used to spend nights and weekends tuning this thing. You'll notice there's a couple things about this. First, this is sort of our 4th varifocal headset that you saw on the wall. Mm-hmm. So by this point, we built this in 2018. We'd started really dialing in things. So, and we also tried to start expanding beyond just what the rift is. So most of this is a rift. So the screens are a rift, but you'll notice if you turn this on the front here, it's got that sort of wide aspect.
Yes.
You've seen this before. It's a wide field, 140-degree field of view. And the way we do that is we take the screens, which are normally portrait, turn them to landscape. So you lose a bit of vertical, but you gain a lot of horizontal. And then we pair that to get the wide field of view with these really big Fresnel lenses. And that was designed by the optics team here. And then we need an eye tracking system for varifocal. So classic, good old IR LEDs.
Yeah.
And then you can see the little bumps down here. That's where the eye tracking cameras are. And then inside of it, there's a little curved hot mirror where it bounces the imagery off. So that gives you the varifocal system. And mechanical engineers, they'd worked on it for years at this point. So really lightweight, quiet, stepper motor based, move the screen back and forth.
Right. And the idea is that, like you said, the whole library works because you're adjusting for it in the SDK, in the compositor.
Yeah, absolutely. So yeah, I could play every game, at least from 2018, because the way we built this, the eye tracker tells the motors where to move the screen.
Yeah.
The screen tells the SDK, hey, the focus has changed, update the distortion while you're time warping. So the game content doesn't even know it's a varifocal headset.
Right.
So you can experience, good old things like Lucky's Tail, Moss, and see all these objects clearly and sharply. Varifocal.
Awesome.
I think the best way to do this is bring the controller up sort of like it's a cell phone you're trying to read.
Yep.
And this is varifocal on. This is varifocal off.
Oh, wow. Yeah.
Varifocal on. Varifocal off.
Oh, yep.
And so again, this is only like a 2100 headset. So it was almost a surprise to many of us that wow, most people get it, right? If the eye tracker's not working or just differences in human vision, but I'm glad you're in the wow camp. The majority of people are.
So what was that experience with varifocal like? After calibrating eye tracking in Half Dome 1, I played some Lucky's Tale and Oculus First Contact, two experiences that let me put objects right up close to my face in my near field. And the demo just kind of worked. I was surprised by how quickly my eyes adapted to the ability to bring objects close to my face and see them clearly and in focus. And I was even more surprised by how quickly I started taking this new level of comfort for granted. And as I soon got to see, there's a tremendous amount of engineering and iteration to get the hardware to that point. All right, Doug, so I got to check out Half Dome 1. That was really cool. But that's not where you guys started, nor is it where you guys currently are.
That's right. No, I was so excited. I'm glad it worked for you. And so yeah, this is really what's inside of the box. So we'll go back to the beginning. This is what we call Half Dome 0. You tried Half Dome 1, which we'll talk about in a minute. Half Dome 0 was literally a modified Rift. So this is the guts of it. You're welcome to hold it. Rift panels, Rift lenses, Rift housing, Rift tracking, Rift. But what our engineering team did is, move the screen. And so you can see here, you can even pull on it here.
Yeah.
So we have a stepper motor, and then we have these guide rods, and it can independently move the right eye and left eye. And then this is my favorite part, little quadcopter technology.
Oh, okay.
So
Yes.
These dampers are helping suppress noise and vibration. You can see a couple things here. First, the total range needed. So we need several millimeters to change the focus from something like 20 centimeters in front, which is in optical terms 5 diopters, all the way out to optical infinity. And so to change that range, we need to move 7, 8 millimeters or so. And so you'll see moments in Lucky's Tale where I look to the horizon and you see both screens slam to the end. That focus is far. Or I'm looking at my touch controllers for some reason, and it comes all the way in.
And that range is based on the lensing parameters.
You got it.
Yeah.
So the lens focal length determines everything. I think the first piece of math I did when I came in the lab is someone was already discussing varifocal when I started even, and the range was the debate. And so just little equations, and you're like, well, it's around a centimeter, which isn't crazy.
Yes, yeah.
And so, the headsets that aren't shown here, that was really the early stuff, is we're like, well, if it's around a centimeter, how noisy, how heavy will that be? This was the answer. And yeah, you can get a sense, even with the top cover removed, even with a big speaker, basically, you can feel the noise and vibration level here. So that's half dome 0. Then this is similar technology, but we're sort of, to be honest, taking a victory lap. We're like, let's push field of view.
Yep.
It's not just for fun on the weekends, it's to stress test distortion. And so same screens, but just on the side. And then wider field of view lens, but otherwise rift components, rift tracking. And
Mechanically, the same principles, but you also have it canted.
yeah, and so since we were pushing that wide field of view, we decided to cant. This is a subtle thing, you'll see this in a little bit, but we also found out, as headsets shrink, you naturally want to have them conform to the face, so you want to start canting them. Canting actually introduces a type of optical distortion that's different, and that starts to make you want eye tracking the more you cant. So this one really it was both the field of view, and I'm glad you noticed it, the canting, where to us, that's a real giant challenge to make the distortion correction look good. When you look at this, you're like, yeah, you canted them, but algorithmically to make that look good was a challenge. And then yeah, in terms of the varifocal mechanics, same stepper motors, same quadcopter technology. That's exactly what you saw in the demo. Half dome 1.
All right.
Okay, enough with the demos. Let's do some real engineering. And so really, this is 2019 work, but we started looking at like, well, look, all of these devices were wonderful, but they were based off of Fresnel lenses. So this is coming out of the original Rift. Big OLED panel, big empty volume, and a Fresnel lens. So you have something like 5 centimeters there. And when you look at a headset, guess what? Our team is the most important. We determine the size of the headset. Displays do, right? They take up most of the volume of the headset. And a lot of varifocal's benefits is comfort. So we started saying, well, this has to go. We have to make the headsets actually lighter and more compact. And so that's when we started moving to pancake lenses. So at Oculus Connect 6, I believe, in 2019, this was Half Dome 2 I'm about to show you, and Half Dome 3. But they're all based around the same optics. So this is a pancake lens where we've folded the optical path using polarization. You've seen these before.
Yep.
We do have a team of amazing mechanical engineers. I'm not a mechanical engineer. This is their work. But they really tried everything. So first, no matter how quiet these could be, even internally, when people hadn't seen this, they'd, vibration must be a problem, noise must be. So they actually tried, even in this era, let's get rid of the stepper motor. There's a lead screw with physical contact that's going to produce noise and vibration. Let's go to a voice coil. And so there, right, you just have the windings, the field pushes the body. And then instead of guide rods where you have that sliding friction, let's just use flexures, little springs. So you can play with that. But you can see this goes about 1 centimeter in its travel range. And everything's tuned to balance the size of the motor, the strength of the spring, to give you what you need for varifocal. So that's sort of this era, and you can see we tried stepper motors with pancake lenses, voice coils. We even tried putting a giant diaphragm spring on the back.
Speaker.
A speaker, basically, and it sounds like a speaker, so this one was out. I mean, this design was clearly a winner.
And to go from rod to flexure here, you can still hold position. You can quickly get to a position, but the eyes, based on how people experience the world, it's constantly shifting anyway.
Yes, exactly.
So you don't necessarily need to hold to a specific
position.
You
don't necessarily need to hold. And if you did, hopefully that you can make the power draw low enough that it's acceptable in the overall system. But it comes back to our team name, it's system. We'd always debated, will it be stepper motor, voice coil, brushless DC motors? What should we use? And all of them have that size, weight, power, cost trade-off. But in this era, for Half Dome 2, we really got excited about voice coils. And here's another variant of it you can see. I hadn't seen one of these before our team came up with it. It's a Flexure Hinge array. So we actually have these rigid members.
Oh, it's on the end. Okay.
Yeah. And so what's cool about this is if you just have flexures, you have to sort of surround the whole body. But here with these sort of rigid members, you can just do it on one side. So you can make the top of the headset really thin. Wow.
But that's all mechanical solutions.
All mechanical. So this was 2019, Half Dome 2. This sort of lens was still what we were working with for Half Dome 3, but this is what's inside of Half Dome 3. So we tried to get rid of all mechanical, all noise, all vibration with an electronic focusing mechanism. So the way this works, at the base, there's a special type of lens called a Panchratnam-Berry phase lens or geometric phase lens. And the way it works is polarized light, depending on if it's right or left circularly polarized, it'll either converge or diverge. So you get 2 different focus settings. And then, so you put that, put a polarizer at the top, put one of these special lenses, and then below it, put a big giant pixel that when you flip it, changes the handedness of polarization. And so now you start stacking that module up. If you put another, so that first layer of 2 things gives you 2 planes.
Yep.
The next layer gives you 4,
Right.
then 8,
Right.
so on and so forth. So this one gives you 32 in total.
It's kind of like a camera lens having multiple elements. And,
Yeah.
But all done electronically.
Exactly. And so, yeah, it's sort of the dream we had. You got some wires coming out that change focus depending on the bytecode you send them, and then just the layers.
And you don't lose a ton of opacity or have a ton of optical distortion.
Everything's always a trade. So the question is, how much do you lose, right? So every layer you add, there's electrodes that absorb. So you'll notice it looks a little yellow. That's because it's absorbing the blue light. And that's something we still work on. Obviously, we don't want the battery to grow.
Yeah.
Because if the battery grows to compensate, now it's just as heavy as these would have been.
Right.
So it's always this game, but we were quite happy with this. We're still working on it, developing it. But you can actually see it here in operation. It's just sweeping through the 32 planes one way and then back. And how this would work, I mean, it's very simple. You would just place this module essentially on the outside. So it's like a prescription attachment that changes focus in a sense. Yeah. Or you could place it somewhere internally if it made sense to do that. So it really was our ultimate goal, is just a handful of grams, a handful of millimeters, but you still have to tie the distortion correction algorithm to this, and now it jumps in discrete steps. So it brings a new distortion correction challenge.
And are you doing experiments with just how many planes you want, period,
exactly.
right? Is 2 enough, 3 enough, 32 is what you have here, is that needed?
Exactly, and so it's the same sort of philosophy you see in our team. First, engineer to its limits. So the first one we built was 64 planes, but then it's at some point, can you crank up the OLED or the LCD enough to compensate, find the sweet spot, and then run people through games? Yeah. Here's 2 plane, here's 8 plane. What do you like? I don't like any of them. Right. Right? So that's definitely sort of the phase we're at in this research of just experimenting with what's the right balance. And I think with Halftone 2, we found the balance for mechanical. If you want to do a mechanical system, something like this for a pancake, I feel this is the sweet spot. We're still finding the sweet spot for this one.
I had a couple interesting takeaways just from the demo I did with Halftone 1, which is the mechanical solution of changing focus. And I think in my mind, I was imagining when you read about all the white papers about shifting focus and solving the divergence accommodation conflict, I was thinking of the cinema landscape and like racket focusing, when you watch a movie and what a cinematographer does. But when I put it on and I use it, it was more of comfort and a sharpness that I got out of that. And just like you said, not having to fatigue your eyes, lowering the strain. That was something I didn't realize was just a natural benefit of solving that problem.
Yeah, I mean, I also think that in addition to gaming and just kind of social presence and hanging out, I think one of the big use cases that's going to emerge over the next several years for VR is just going to be doing more work in it, right? So whether it's workrooms type meetings or, basically, I think that probably by the end of this decade, we're going to replace our workstations on our desk with a VR setup for a lot of things. It's just going to be better for way more use cases. I mean, you're going to have, the screen can be as big as you want, or you can have as many monitors as you want. You can carry your VR headset to a new room, but basically have your perfect desk set up just right there. But when you're doing work, reading is a lot more important. And when you're reading, being able to have a closer focal distance is also pretty important. So, so I mean, you can do it, reading on a monitor on your desk at a meter away from you. I mean, that's what a lot of us do today. But I do think being able to have that be dynamic is going to be really valuable. So, to me, I think it's not just a comfort thing, but I think it's going to unlock a lot of functionality that is that's pretty important too. And certainly by the time you get to having AR glasses, or you're kind of sitting on your couch and you're reading a book, you're not going to want that a meter away, right? You're going to want that, maybe a foot and a half or a couple feet away, like you would read a normal book. So I think for that, having varifocal is going to be really important.
Yeah, yeah, and talking about this productivity and that kind of infinite computing environment, Mike Airbrush at previous Connects had that's the thing he keeps on bringing up as like his guiding star, which is really interesting. And even legibility, so resolution, obviously, is one of the
Yeah.
things that people just we understand it, right? We understand it with cameras, we understand it with traditional flat screen displays, even TVs. But what does something like the Butterscotch prototype help you think about?
Yeah, so this is the Butterscotch prototype. It's a different one. It's basically a modified. It has like a Quest 2 frame, but it's or a Quest frame, but it is a high resolution prototype that gets to 55 pixels per degree across your field of view, which is significantly higher than anything that we're kind of producing today, or anything that's a VR product at scale. And the goal of this prototype was really to give a sense of, as you keep on improving the resolution, where is the diminishing marginal return point, right? So if we're at around 20 ppd in Quest 2, every generation that we ship improves 10, 15, 20%. So it'll just naturally improve a lot over the coming years. But as you get to 30, 40, 50, 60, everyone's eyes are a little bit different, but I think for a lot of people, retina level resolution is going to be around 60 ppd. The question is, what new functionality does that unlock? Is it a noticeable difference? And one of the big differences, again, is going to be text and just reading. You mentioned legibility. You can get to legible text actually at a lower resolution, but it looks a little blurry. So there's a difference between legibility and comfort. And for something that you're going to want to be in for a long period of time and where the text just looks beautiful, you are going to want a kind of higher resolution display. And again, this is a much harder problem than screens, because if you're thinking about like the anti-aliasing, for example, on a screen, it's perfectly geometric. The lines are perfectly horizontal. But if you turn your head a little bit here, then you're going to be reading text, and
Right.
it's going to be a little bit of an angle, and it's going to, every frame might be at a slightly different angle. So having the screens be really good and having the whole graphical stack be able to support that is a pretty big deal. The other thing I'd say about this that was a big takeaway is things like text actually are relatively a lot easier to render than a whole 3D environment. So by the time you start getting up to such a high PPD and resolution, you start getting a lot more limited by the software and graphics stack to kind of power the display than just what the display can do itself. Just because it's so many pixels, and you're basically trying to power this by chips that you can fit on a headset on your head, where you want the battery to last for hours and not get drained immediately. And it would be possible for GPUs, especially if we kind of crank this so high, to just run so hot that it actually just was too hot on your face and was kind of physically uncomfortable. So a big part of what we need to do is not just get the displays to work well, but also optimize the rendering and the whole graphics stack, so that way we're doing that as efficiently as possible. And there's a bunch of exciting stuff if you want to kind of rat hole on that. The way that the human visual system works is basically we don't render, or we don't see the whole world in the same resolution, right? It's, we look at something, and what we're focused on we see in a high resolution, but things around our peripheral vision are much lower resolution. So, if you had all these pixels in like a 55 ppd display, one of the tricks that I think we're going to need to get to is, what people call foveated rendering, which is basically the idea that you render what you're looking at in a very high resolution, but you can relax the resolution around the periphery. But of course, in order to know what you're looking at, you need pretty much perfect eye tracking, right? Because, in order for the whole system to work, it needs to kind of, the display needs to kind of update and refresh within, 5 or 10 milliseconds. And as your eye is moving around, you basically need to have a system that can almost predict as your eye starts moving where it's going to end up. So that way you can start rendering what the world is going to look like at that point, if you want to have any hope of just doing the stuff that your eye is focusing on in high res and the rest in a kind of a lower res peripheral vision. So between pupil steering, eye tracking, foveated rendering, you can kind of hope maybe to get to an efficiency on the compute and graphical stack that you can start to power a lot of these much stronger displays. But I think this is an area too where I'm pretty confident that each generation that we ship is just a bit better than the one before it, and I think we're headed towards high resolution over the next several years for sure.
So to pass the vision Turing test, one of the key challenges is to advance the resolution of our headset to match the full potential of human eye.
Sure.
And the most sensitive portion of human retina has a resolution of about 60 pixels per degree, so 60 ppd, which is often referred to as 20/20 vision. In order to achieve that, well, Butterscotch headset can almost achieve that, and this is done through using state-of-the-art display panel and also a custom-designed lens, so that the lens can fully resolve the pixels and high resolution of the display panel. And inside the lens, we used 2 high-precision glass lenses, and you're welcome to hold them. So they're glass, so they can mate with better surface quality, but also at the cost of some weight. And also, we include a special lens that instead of refract lights like glass lenses, it diffracts light. So it's the similar type of lens that you saw in the Half-Dome 3. And you're welcome to hold it. So it disperses light in the reverse order compared to glass lenses. So the combination of them can create a very sharp image for the user. And you may see 2 sets of images because it's polarization sensitive, so natural seeing is unpolarized. So in the headset, you only see 1 copy of image. The other aspect of the headset is that it has lower field of view than kind of common VR field of view, because imagine we're trying to support 60 pixels per degree for full VR field of view, say like 100 degrees. We need 6,000 by 6,000 pixel per eye, which is beyond the state of the art of display of this size at the moment. So we had to reduce the field of view to less than 60 degrees to support near retina resolution. So that makes this one a time machine, so that we can kind of take a peek into the future, see what it looks like, and see what the experience is like with retina resolution, and think about what we can do with it.
This Butterscotch demo was fascinating because it allowed me to manually simulate pixel density from the quality we have today on a Quest 2 all the way up to 54.5 pixels per degree, close to 20/20 vision. I could see that once we passed 35 ppd, text rendered about 2 meters away was easily readable. And at the max ppd, it was far and away the sharpest image I've seen in headset. A virtual eye chart posted at the far end of the room was completely readable and clear. For me, it wasn't even that the text stood out the most. I started to get enamored with textures on objects in that room, the vividness of the wall art or the pillows on that virtual couch. I couldn't stop looking at them. And even though the simulation of lower PPD wasn't a direct hardware comparison with the display systems of headsets today, the real-time adjustment gave me a sense of the benefits of lowering render resolution on high PPD hardware, and where there's an opportunity to find a sweet spot between rendered resolution and panel resolution. So like these prototypes, as the team brings them to you, they are full systems, right? It's a display systems research team. It's not just the panels, it's the optics. And then they give you confidence in how you can project out something, whether it's 5 years away or 10 years away. Is that how you kind of look at
although
what they're showing
the
you?
research teams, we try to isolate one dimension at a time. So, maybe they'll do something in a headset that in theory we would try to get into a Quest wireless headset in the future, but maybe for Butterscotch, I think the demo I did was wired into a tower PC, right? So that way you have all the compute necessary to drive this thing, so you're not trying to solve all of that and trying to squeeze the performance out of the mobile CPUs and GPUs that are available today. So I mean, these demos are really primarily focused on the display tech, while understanding that we're also going to, we have other areas of research that are focused on graphics pipeline, sensors, how to do the eye tracking as well as possible, pupil steering, all the things that we just talked about are kind of different areas of what we need to do as well.
Yeah, and something like optics, which is married to display and changing even one dimension of a display variable, getting a new display in means the optics will have to change. I saw that there's as opposed to manufacturing optics, you can simulate the optics using a simulator, and can you talk a little bit about that kind of what DSR is able to do in iterating and in creating simulating optics and simulating displays.
A lot of how I've tried to run the company is I want us to learn as quickly as possible, right? So a lot of why I love software and being able to iterate quickly, it's not just that moving quickly is fun, which it is, but it increases your feedback loop, right? So you can get something out to people, and then you get feedback from real customers and people about what they value, what they think actually wasn't as good. And I think one of the things that's sort of unfortunate about hardware development is just the cycle times are so long that we have an idea for what we want to do and maybe some future headset, and we're not going to know if people really think it's amazing or if they valued one feature over another for multiple years after we start working on that. So if you can shrink down that cycle time, especially when you're doing research, it's really helpful. So yeah, so some of the simulation stuff is really good. One of the areas that we've worked on that is specifically helped a lot by this is optical distortion correction, which I think we talked about a bit before in term, and you probably saw some of this in Redmond as well, where there's this dynamic where as your eye is kind of moving around and looking through the lens in different directions, there's different kinds of distortion in the lens that we need to correct in software. And the more that we can basically model out the lens, and kind of work on new models of the lens to improve that, the faster we can iterate on the software for the optical distortion correction and things like that just make the little kind of quirks and errors in the way that the display would work that they're usually not so bad that they kind of look terrible, but they're subtle enough things that it takes away from the feeling of realism or maybe makes the experience a little less comfortable when you're in it for a while. So that's certainly an important dimension of this too.
Mm. And that feels like that's a dimension that you can't rely on a partner or supplier, that you have to do in-house, whereas things like displays or compute, it's you look at the roadmaps of partnerships.
Yeah, I think that's right. On the distortion correction, I think that's primarily a software thing. Although what I notice, we work with partners on things like compute and silicon. I mean, we work with Qualcomm on the chips and other companies as well. But compared to the displays, I think one of the things that's worth noting is that this is like a completely different display stack and technology path than what we've had for phones and computer monitors and TVs for decades now. So in a lot of these cases, and we ultimately work with different partners to manufacture a bunch of it, but a lot of this is very novel technology that you can't just buy off the shelf, which is why in a lot of cases, and especially as a lot of this research starts making its way into products, the headsets that we make are just going to be pretty far ahead of what anyone else can make on the market. So this has been a long-term investment, but I care a lot about this because it helps deliver this, realistic sense of presence, which I think in a lot of ways is like the holy grail of social interaction, which is sort of what we're trying to get at Meta.
Yeah. I remember the first couple generations of VR headsets really were able to piggyback off of existing display tech, things that were already at scale, like in phones, in IMUs and sensors like that. But increasingly, things have to be custom. And so it sounds like the research teams kind of inform how you make those investments to know, what kind of needs to be the foundations that need to be laid down today, so that 10 years from now they're ready. Yeah,
that's right. So I think that you can use some components that are shared from like the mobile stack for VR. For AR, that's almost just completely different. The display, there's not like a traditional screen in that at all. You just have a projector and a waveguide, and it's people just haven't built the kinds of things that need to exist for good AR glasses in the form factor that they need to exist in before. So that's like completely novel stuff, which maybe it's part of what our teams do is work on the display tech across the whole line of different things that we're working on. But yeah, there's a lot of novel stuff here that needs to get invented.
So these are 3 different lens modules from different headsets, and they represent the 3 headsets that we'll be simulating in just a little bit. And you can tell that they're all quite different shapes. This one's a Fresnel lens from Quest. This is a pancake from Half Dome 2, which is a successor to the Half Dome that you saw earlier. And this is a holographic pancake, Holocake 2, which you'll see at the end of the day. They look pretty different, but conceptually they basically all work the same way. There's a display on one side. You look at the display through the lens. And when you do that, these optics introduce optical distortion to what you see on the display. And so this is an example of that here. On the back, it's just a regular grid, but you look through it, you see the distortion. And the thing that I really want to draw your attention to is the fact that the distortion changes as your eye moves relative to the lens, and you can see that there. And so, in consumer VR headsets today, we can address distortion through something called static distortion correction. You take whatever it is you're going to render on the display, you warp it, and then when you see it, it looks mostly okay. Yeah. But what we can't address right now is that dynamic distortion that you saw when you move the lens. Your eyes are always going to be moving around when you're in VR. And so if you have an eye tracker, if you can update your eye position, using that eye tracker, then you can update the dynamic distortion. You can update the distortion correction dynamically, and then you won't see any more distortion. If we want to study what distortion is like inside a headset, then you might think that you'd want to experience the distortion in a headset, throw in an eye tracker, and see how well dynamic distortion correction worked. And that could be one way of doing that. The problem is it takes a long time to build these things, right? Yeah. And so if we wait all the way until the end, we build a new half dome, we build a new holocake, and then we try to see what the distortion looks like, that's not always the best way to approach things, because we've lost out on a lot of time from waiting for that thing to be built up. And then on top of that, even if we could build these things a little bit faster, you still wouldn't necessarily want to study distortion inside a headset, because you and I, when we put on a headset, they fit us differently. And so we might see different distortion. And so it's not a great place to be in if you're trying to run studies that require high precision and reliability. And so that's why we ended up building the simulator here. It addresses both of those problems. So we want people to experience distortion in VR-like environments. And so we have this giant TV. We put it really close to somebody's head, and that gives us wide field of view. We want the 3D aspect of a headset, and so we have these active shutter glasses. We've synchronized them to the TV, and we basically recreated 3D TV technology from 5 to 10 years ago. And we want head and eye tracking, and we get that with this rotating chin rest here. And so you can see, as we rotate the chin rest, we have a model of somebody's head and eyes. And right now this is called a vestibulo-ocular reflex eye movement, or VOR. It's an eye movement that we think really highlights distortion. And the nice thing about VOR, in addition to highlighting the distortion, is that if we know where somebody's looking, if we have an accurate model of the head and eyes, then we get head and eye tracking kind of for free just by knowing where their head rotation is. Cool. And then you can see in front of these eyes here, we have these virtual lenses, and that's what allows us to actually simulate the distortion. One of my colleagues on the team wrote a nice package called Light Field Portals, and that allows us to simulate different lenses just with the press of a button.
Right.
And so we can basically simulate an entire headset in software instead of having to build the thing.
Yeah.
And then the last part is, because this is all in software here, we're not restricted just to simulating the different aspects of the lens. You can see here, I can just change, I can change the cant angle of the display. And so that means I can take those headsets, wrap them around my headset to achieve better form factor, but that might come at the expense of distortion. And so using the simulator, we can explore all of those different options, all without having to actually build anything.
This optical distortion simulator and Phil's explanation really hammered home the challenge of engineering display systems. Every time the DSR team experiments with a new resolution, field of view, or varifocal solution, the optics introduce distortion that have to be compensated, and in a perfect world, calibrated on a per-user level, as each of our eyes are different. And it's these delicate trade-offs that need real-world testing to achieve a sweet spot for user experience. Next up was the demo I was most excited to check out that day. The Starburst Prototype demonstrating true high dynamic range using a backlight 200 times brighter than that on today's headsets.
One of the things about the real world that we need to mirror in VR in order to achieve this visual Turing test goal is to recreate the full range of luminances that we see around us. So one thing that I like to do is just kind of give people some framing around how bright things actually are, because we don't often measure these things. So this is a Luminance Meter. It measures things in nits, which is sort of an industry standard for display brightnesses. So I'll start by just pointing out on this monitor here, we have this white area that you'll see. It's a stage light that's in VR that you'll see in a minute. If I measure that on the monitor, you'll see that it's a little bit under 200 nits, which is pretty common for just a standard desktop monitor.
Yep.
Not very bright. The whole room here is not very bright either, but if we measure this fluorescent light that's up here, actually I guess it's an LED light, 11,000 nits.
Wow.
So yeah, quite a bit brighter, and you wouldn't be struck by how bright it is. And then of course outdoors it's significantly brighter. So what this is an initial pass at trying to reach these full indoor luminances so that we can start doing user studies and start to understand what brightnesses are necessary to kind of unlock a greater immersion, better feeling of realism. So you can go ahead and take a look inside.
All right.
You'll want to. You can either remove your glasses,
Yeah,
or we can check out the facial interface. Should work.
Okay.
And you'll want to get yourself seated so that you can find the sweet spot in the middle of the lenses.
Yep.
And then you'll look at this little sphere. We have this very simple scene that's just going to be showing you a reflective chrome material and some lights. And right now it's set at 100 nits, which is pretty close to where current VR headsets are. And if you look off to your left or your right, you'll see these little stage lights that we saw on the monitor a minute ago. And you can tell that they don't really, it looks like a picture of a light. It doesn't really feel like a light. Now I'll bump this up to 1,000 nits, which is where you get like a nice HDR TV right now is about this level. So you can, think about how the ball maybe feels a little shinier, how the lights feel a little bit brighter, but it's still not all the way there. So now we'll go up to the full brightness of this headset, 20,000 nits. And now it should feel like you're actually looking at a light when you look over there instead of a picture of a light.
And I can physically feel my eye adjusting to it.
Yeah.
As I shift between them.
So this is a really simple scene for the purposes of making this comparison. But if you switch it to the 20K nits, or you're on 20K, and then turn around to look behind you, I also have an HDR photo here, which this is now giving you this greater immersion that you're getting your wide field of view, binocular cues, and so on. But now you're also getting these luminances that your eye responds to in a different way than if it had all been below 100 nits.
Wow. And this is just static image, standard HDR with the metadata layer of luminance.
Yep. Yeah, so this was just captured with bracketed exposures in a standard way.
That's such a big difference.
So you mentioned that you sort of feel your eye responding to it in a certain way. And we know that there are a variety of perceptual cues that you get from that expanded luminance. And part of that is due to work that was done for the display industry for televisions and cinema. But of course, when you have a more immersive display device like this, where you have wide field of view, binocular parallax, and so on, we don't know if the perceptual responses actually map directly from the prior work that had been done with TVs. And so one of the reasons that we've built this to begin with is so that we can start to unravel where those differences are, where the thresholds might be, where you start to feel like you're looking at a real light instead of a picture of a light, which will then eventually lead us to being able to build devices that then content creators can actually produce content that makes use of this full range and gives you this more immersive experience.
So Nathan, one of the reasons like this is like this 5 or 6 pound thing is here. You said there's heat sinks, there's fans, but the backlight, they're not traditional backlights, right?
Right.
So can you talk about that light source?
They are traditional backlights in that they're LEDs, which any LCD display would have, but usually those are on a strip along the edge, and then there's some little light shaping wedges made out of plastic and some films and things that kind of make it uniform to come out. But they're relatively dim compared to what you'd have in a room light or a video light. And so what we've done is actually taken the same kind of, they're called chip-on-board LEDs that are used in video lights, and put them in there, replacing the original backlight. And so it's very simply just turning up the brightness on what's coming through the LCD. But as a consequence, now you've increased the size and weight and power requirements and so on in order to be able to do that.
And when I'm in the tens of thousands, like 20K nits, is that what's being emitted by those backlights, or is it even brighter because it's being taken down?
Yeah, it's even brighter. So that's like a full light that you would get in a video kit or something like that. And then the LCDs cut it down to maybe 1 or 2% of the total, even when they're in their full clear state.
Wow. 1 or 2%
of the original light.
Really?
Yeah, exactly. Because you've got polarizers, you have the color filters, and all of these things absorb a lot of light. So there are 2 LCDs back to back here in order to get the higher contrast. If you just took one LCD and turned up the backlight to that level, you'd get brighter brights, but you'd also get brighter darks because LCDs have some finite contrast. And so by stacking 2 of them together, now we get that extra. Instead of an 8-bit display, now you have a 16-bit display essentially.
Yeah, I never thought of that. How people think about the limits of an LCD, just stacking them, increasing the backlight, which you have to do anyway here. But then you get full range of contrast.
And so there's the 2 HDMI cables, 2 power supplies. There's a tracker, and then the little thumb buttons that you're using are all routed and plugged into a PC. This is the heat sink and the 2 LEDs that form that backlight that we were talking about. So there, you can kind of see them through there. That yellow is actually a phosphor, which a lot of these room light LEDs use to emit a broad spectrum white light. And then there's a little Fresnel lens on top of it to kind of steer. So they're designed to emit, a hemisphere of light. This is to steer it in towards your viewing optics, so you have less light bouncing around where you don't want it to go.
Optics just for the backlight.
Just backlight optics.
On the other end of the stack.
And the heatsink itself is actually 3D printed with metal sintering to get a lot of surface area in there. And then you can see that it's been machined down for some of the mounting points that need a little bit more precise mating with the other components. So a lot of the weight is there in the headset.
But it's still a lot lighter than if it wasn't SLS printed with this configuration to disperse the heat.
Yeah, exactly.
And I can see that, the standard COB LED that you could buy to place a car headlamp or something.
It's exactly what it is, So then we have this, this is just another heat sink that so the whole chassis is basically a stack that all bolts through on these 4 corners. That's just a heat sink, and it gives it the proper spacing between those shaping lenses there, and then there's another pair here that together steer the emission cone in through
evenly across the display panels.
And then the 2 display panels are already mounted in here, and you can kind of see here's one of them. The front one here is a monochrome panel, and the rear one's a color panel. And these are actually from consumer resin 3D printers.
No, usually mono LCDs.
Yeah, because it's a way to get a transmissive LCD and a mono LCD for that. In that case, just without having to
masking.
modify
That's how you get the pure black levels. It's a mono LCD.
They've been designed for high contrast.
Exactly.
Because you need that in the printer.
Right.
And so those are stuck in there, and then you can see we've used a low reflectance black paint airbrushed on here to further reduce the stray light. Because once you've gone through the LCDs, now we have our image. And now we really want to take care to preserve the contrast that we've gone through all this effort to create a high contrast image. Now we don't want it bouncing off the aluminum. Even though it's anodized, it's still not as dark as you get from this kind of paint.
Right. And that's you're painting this just absorbing light, absorbing any of the spill.
Yep. Yeah. Trying to control those unwanted paths as much as possible. The final part is just an eyepiece like any VR headset. We've done more light management here with these little baffles and more of that paint. And then these are just a pair of off-the-shelf lenses. These are not Fresnel lenses like you'd get in a commercial headset for which reduce your overall track length, and that's just because those resets on the Fresnel lens add a lot of scattering.
You don't want the God rays,
Yep.
especially, yeah.
Because again, we're trying to keep the contrast that we created, and so these are just conventional achromatic doublets that have pretty high contrast at the expense of a little bit higher offset from the LCDs.
And you're not bound by any form factor, but this is what's necessary
Right.
to get
Yeah.
20K nits.
And that's true for a lot of these experiential prototypes. If we're trying to study some particular perceptual effect or something like that, we have the luxury of relaxing all of these other constraints so that we can really dive down along that one axis and learn something that we wouldn't be able to with something that was more balanced across.
Yeah, I mean, I'm curious, what did you think of that one? I mean, you'd mentioned before that.
Yeah, that was the demo I didn't want to take off because, even though it was a simple scene, it was a static sunset and like kind of a chrome sphere with some lights, it looked more believable. I think, there was this aspect of, like you said, the visual Turing test where there was a believability to it, even though it didn't need to be retina resolution, but looking at just luminance and looking at almost, it created depth even. Because you're looking at highlights on a photo or highlights on a movie. Things kind of look flat on a traditional laptop or phone.
Yeah, and it's I think not what a lot of people would expect. I think most people, you'd guess that it's like, oh, getting to retina resolution is going to be the big deal, or I want to be able to focus at all distances, or having a wider field of view. But I think a lot of people have the experience that you're talking about, which is actually the brightness creates a depth of its own that actually is more convincing than even having a higher resolution display. So that I think is somewhat counterintuitive to a lot of folks. But this is also, I think, going to be one of the dimensions that's the hardest to really get to, because at some level, I mean, the light is just energy, and energy comes from a battery.
Yeah.
But I mean, talking about how this dovetails with other parts of the tech. I mean, one of the technologies we talked about before was pupil steering, right? To be like extremely accurate eye tracking that can kind of track exactly where you're about to look. And today, with the displays, they send off so much light that actually doesn't go directly into your pupil. I was talking to Michael Abrash, our chief scientist, about this before, and he was sharing that actually most displays are less than 1% efficient in terms of the light that they emit going into your pupil. So if you want to kind of think about what perhaps one of the likely paths to getting to 10,000 nits directly into your pupil is, it's getting to very accurate eye tracking and pupil steering, and then having a display that is more focused and can basically pipe the light directly into your pupil. Then you can potentially have that much light in a way that isn't going to completely drain the battery or generate so much heat that it feels uncomfortable on your face.
We're talking about bypassing the trade-offs that you have to make by implementing the other dimensions of the visual Turing tests and the lenses that just are a little more opaque because there are electronics or polarizers in them.
Yeah, I mean, all of these things have different levels of efficiency. So, I mean, the more light you're losing through them, the harder it's going to be to get to 10,000 nits. I mean, VR displays today aren't even 1,000 nits. So,
right.
I think things like the pancake optics that we're working on for the Project Cambria that's coming out. I mean, that's actually it has a higher resolution, but it's actually less efficient on light than the Fresnel lenses that we were using for Quest 2 and the previous devices. So we think that we can improve the efficiency of pancake optics to be able to get that to be higher. But even there, that's just the amount of light that passes through, not the percent of the light that's directed into your pupil. And if you want to get to 10,000 or 20,000 nits into your pupil, I think having it more directed is going to be helpful. So, I mean, these are some of the directions that we're basically researching and looking into. But I think realistically, this isn't stuff that's going to show up in the next few products that we ship.
Yeah, and in Project Cambria, that's when technology and research gets into product, and even something like the hollow cake, prototype that you guys are working on. for that one, it seemed like form factor was important. That
Yeah.
the parameters of form factor start dictating what technologies are able to fit in the headset.
Yeah,
Can you talk about that prototype?
Yeah, so this is the HoloCake 2 prototype, and yeah, it's the form factor is really good. I mean, in terms of comfort, it's not just visual comfort, but you want to have it be light on your face. There's a difference between kind of the effective weight and the actual weight, in that a lot of VR headsets are kind of thick in the front. And when weight is further away, it's like a seesaw or a lever. Weight that's further out, you actually feel more pulling your head down than weight that's closer to your face. But the thickness of the lenses, so the Fresnel lenses, are a lot thicker than the pancake lenses that we're going to ship in Project Cambria. But you can get even thinner with what we're working on with HoloCake, which is it basically uses this holograph technology that it sort of mirrors the way that the light would get focused going through a lens, so that you can get to a much thinner lens, much lighter, better form factor. But we think that, I do think one of the trade-offs in this specific design, which by the way, I think that we have this rigged up, so I think you can actually connect it to a computer and play PC VR games on it. In the near term, the efficiency is a little bit lower. So we're working on ways that you could potentially power this in order to make it more efficient. But that's why this isn't kind of shipping today or in the next couple of generations. But it's a good sense, I think, of basically like where things could go. Maybe a little later this decade in terms of the form factors that we'll be able to achieve.
So I was able to play games with the first working demo of the HoloCake prototype, running tethered off of a desktop PC. And while the in-headset visuals were comparable to that of a Quest 2, I was really struck by the lightness of the form factor. When I put my hand up to my face to adjust the headset, it was so startling to forget that there was no typical headset bulk sticking out from my eyes. I think once pancake lenses become standardized, it'll be difficult to go back to the form factor used today. I could say the same of all these prototypes that Doug and his team have created. They did act like time machines that gave me a glimpse into what VR could be like in a decade's time. But while they show a glimpse of that future, they don't give a technical roadmap to getting there. And we just have to trust in the confidence of these scientists that it's possible in a practical and affordable way. And how does Meta choose to prioritize these different features as they look to incorporate them into future products that you and I can buy? Mark was able to speak about that, and as well as how this research crosses into augmented reality products as well. And it seems like, from form factor or pushing one of the dimensions to an extreme, to 20,000 nits, to 55 ppd, your team gets to learn a lot, whether it's where the diminishing return points are, or where people are going to still want more. I mean, like, is that like the push and pull of, like, it feels like users' experiences are going to be able to push the limits of whatever the hardware can deliver, no matter what.
Yeah, that's right. And I mean, I think at this point we're pretty convinced that people are going to want improvements in all of these directions, but what use cases each one unlocks will affect how we prioritize getting them in. And then, of course, there's all this new technology that, it's also, we want to try to get something that can fit in a good form factor, which is kind of what we showed here with HoloCake 2, and also you want the price to be affordable, right? So I mean, I don't think we're not trying to produce a $5,000 VR device. I mean, we want to do something that people can widely use. So we're trying to just improve on this each generation. The different dimensions will get better and better. But the point of the research team is to kind of imagine what are the problems that we're going to need to solve for the devices that we're going to be building 5, 7, 10 years from now to really be a lot better.
Yeah. Do you envision a world where you would mandate or want all these dimensions to be achieved at a certain benchmark in one device, or a family of devices? As Quest 2 will live alongside Project Cambria, they kind of serve maybe different purposes.
Yeah, I mean, hopefully, eventually we'll be able to get these all into a device that that most people in the world can afford, just like most people have phones. But yeah, I mean, I think when you're introducing new technology, there is this this pattern where, especially when you're producing stuff for the first time, new screens, new types of things get cheaper to make as you make them in larger volumes. So when you're first ramping up, whether it's waveguides for augmented reality or, some of the components here, at smaller volumes, it will be more expensive. But I think that there's this difference where, for most people who are doing it for consumer use cases, so hanging out with friends, playing games, maybe things like fitness, I think that there's a certain price point that you want to get to. But if this is like your workstation at work, I mean, I'm just thinking about, it would definitely, we buy, all of the engineers at Meta, pretty expensive computers in order to improve their efficiency. And, I'd certainly be willing to do that. And get a top of the line VR headset if that were going to improve every engineer's efficiency by a few percent in the code that they write, or how they work together. So I think that there are going to be two different basic price points, and I think more of the technology will be able to come into the kind of higher, more kind of professional grade, work-oriented one first. But even there, I don't know that people are going to want a $5,000 device. I think it's probably more around what you'd pay for a PC today. So there are going to be limits on this, but yeah, I would certainly expect technology to be introduced at the high end and then come down to the consumer level. And we care about both because ultimately we're a company that's one of our differentiators is that we're not just trying to produce luxury items. We're trying to produce products that billions of people around the world can use. And of course, if you're doing that, you both need to advance the state of the art on technology, but you need to get it to a point where it's affordable for everyone too.
Yeah, and then one final question is, how much does this technology keep one foot in the door or one eye to its applications in augmented reality? I mean, with whether it's through pass-through plus, or next generation of that, does the research team kind of operate solely for the visual Turing tests in VR, or how does that kind of intersect with the AR development?
Yeah, I mean, a lot of the components are going to be pretty similar, but a lot of them are different too. So, some of the things that we talked about, like eye tracking, is clearly going to be very important in augmented reality too. If we build displays that can, more directionally transmit light, I mean, that could be useful across both, although I'm not sure exactly how that'll play out over time. I mean, there is this direction around mixed reality, which I think is different from pure augmented reality. Pure augmented reality would be, you have normal looking glasses that you actually see through, and you're getting the photons from the physical world. Whereas pass through is you have something that looks like ski goggles. You have cameras that capture it, hopefully in pretty high resolution, and then you kind of print those onto the display, so you're getting the physical reality passed through into your digital screen. I think some areas of that may be overlapping, but the display tech and the graphics pipeline for how that works is going to be pretty different between mixed reality and augmented reality. But there's a lot of shared components, and the advances on how we render 3D objects and just how we can squeeze as much performance as possible out of that. I mean, that's kind of a shared tech stack, and there will be a shared development platform. So you can imagine that people, developers and creators, will build stuff for augmented reality, and then it'll run in virtual reality too. So I think that's going to be a pretty exciting part of the future, is just how this stuff can kind of transfer across all of this different tech.
Very cool. Well, thank you so much, Mark. It's even though we're in the early days, these devices I got to try out were little time machines, as the team described, and glimpsing 5 or 10 years in the future. It was really neat to try them out.
Yeah, exactly. All right. Well, yeah. No, thanks for having me. I'm glad to get a chance to talk about this stuff. I'm pretty excited about it. It's this is just one part of the stack that we need to deliver, but I think hopefully the sense of just how deep even this dimension of this goes, and the depth of the work that we're doing on this serves as an interesting example for all your viewers around just how focused we are and how deep of kind of a research and product development program, and how ambitious what we're trying to get done here is over the next 10 years in virtual reality and augmented and mixed reality, And we didn't even talk about any of the neural interfaces or any of that kind of stuff, which is its whole own awesome zone to be in. But I think that this is some of the most exciting technology that's getting developed today, and I'm glad that I had a chance to share some of it with you.
I really appreciate it, and you have a great team working there as well, so please extend my thanks to them as well.
Absolutely. All right, see ya.